All right, so we're going to continue our incredibly exciting journey into periodic table basics. Um, if you've already seen that lovely riveting metals versus nonmetals metalloids work of art that should change your life, we're going to continue on and dig a little deeper and take our most broad category of metals, nonmetals, metalloids, and start looking at rows and periods versus groups in our columns. So this will be mainly focused on our groups, which we also call families in the column form, as opposed to periods. That's something that we actually dive into a little deeper when we get into electron configuration in atoms, where and how electrons are flying around that nucleus. But in this video, we're going to see new vocabulary. So we classify these elements into what we call families, okay? And we call them families because if you look at a periodic table, every element that's in the same column or group is considered a family, because every element that is in that column or group will share a very important characteristic that makes them, we'll say, related when it comes to chemistry. Yeah, there's a lot of differences. So obviously these atoms are much bigger than these when it comes to elements, but they do share something very important in common we're going to learn about that makes them connected. And so we put these in the same column or group or family because they react similarly. So whether it's large, small, the way that they tend to behave, bond, and react is very similar. So we say they're part of the same family. So when we're going through and looking at our families, we get new vocabulary such as alkali metals, alkali earth metals, or alkaline earth metals. We already saw transition metals a little bit. Well, I've talked about them in different places, but we'll see them a little more in depth here. So what are these things? And then we have discussed metalloids, semiconductors, in a previous video, but then we have halogens, and I keep needing to change that. Don't know where we came this. Nobel is a prize that we get for discovering noble gases, I suppose, but that is, forgive the omission for the spelling error. But this is our main purpose. When you leave, I want you to know when we say group 1, we're talking about alkali metals. Group 2, alkaline earth metals. And then transition metals, we don't even bother group numbering, and you'll see why. And then group 17 are halogens. Group 18 are noble gases. And then down here, relating the properties to the electron arrangement. This is going to be the problem, y'all, and I'm just warning you. First time I did this video, I think it ran almost 30 minutes because it was very difficult to go through this without digging into electrons. Because at the end of the day, the whole point of the periodic table, as we're looking at it, it is a tool that we use to be able to explain so many things about how any given element behaves. And you can tell story after story after story just based on this element's location within the periodic table. It is layered information. So I give my students multiple periodic tables that we color code, and they're all very true. And you can see you can use the same arrangement, same periodicity, the repeating characteristics that we get as you move across the table that create our columns. You can go for days with things that are hidden within the table. But what we're really going to spend a lot of time with is what it tells us about the electrons, because that then tells us about bonding. What kind of bonds do these elements want to make with one another? Do they want to make bonds? And we can do huge predictive action knowing where they are on the periodic table in terms of what they're going to want to do. And that is a really, really valuable tool. But it all hinges on electrons, and we're not quite there yet. So as I'm going through these notes, I'm very tempted to talk about valence electrons. Great word. But what is it that makes valence electrons so important? Because all of an atom's electrons aren't necessarily valence. So when we see this term, what does it mean? We are so close to getting there. But I'm going to try to be very disciplined and not deep dive into wanting to give you some super spoilers for electron worlds. But first family we look at, now I'll try to make this quick. Every time I say that, I jinx myself. Group 1, and I will very quickly, let's see. That's fine. If it's a pen. I like to call these group 1 metals, with the exception of hydrogen, because it is not a metal. But group 1 or alkali metals are very special because they are our most reactive metals on the planet. So in terms of watching them interact with other atoms, they are very, very energetic and reactive and very willing to form bonds, and they are desperate to be able to change. So you ask your question, why is that? Why are they the most reactive? Well, stay tuned, okay? But for right now, just start with your scaffolding of knowing group 1 alkali metals are important because they're the most reactive, okay? So you'll see them in the examples we do. We'll just pull from group 1s and group 2s constantly. Let me give you a little eraser in action here. Whoop, whoop, whoop. So, as we will see shortly, our group 2 metals, alkaline earth, come on. A lot of times you'll see that with an Ne for alkaline earth metals. Group 2, you're going to love the creativity of this, and please don't mock, or feel free, I'm not there, so you can mock me all you want. But I'll probably feel the self-esteem hit from here. Special nature of alkaline earth metals, or, as I like to say here, group 2 metals. So I told my students today, I tend to refer to alkali and alkaline earth as group 1 and group 2. Maybe it's just the difficulty of saying it. It's a mouthful, alkaline earth metals. I'll just spit out group 1, group 2. So, magnesium is a group 2 metal. Sodium is a group 1 metal instead of alkaline and alkaline earth. But we like to be official. So alkaline earth metals are very reactive. So like their cousins over in group 1, they're also very reactive metals, very quick to be able to find something to react with and show some energy. But, are you ready for this? Don't mock me. They're not as reactive as group 1 or our alkaline metals. So, what do I want you to know about alkaline earth metals? Well, they are and an INE, number 1. Let's make sure we're doing justice to that. But they're very reactive, and I'll actually add in here, they are, same thing for group 1. They're very predictable. So when we give you these metals and these elements in a problem, We give them very frequently in problems because we know how they're going to behave. There is not a question as to how group 1 or group 2 metals are going to behave in a reaction. They have one personality when it comes to reacting, and that may seem boring, but it's very, very nice when it comes to predictability. We like predictability. So if I'm giving you a problem, it's good to give you things that you can take to the bank in terms of knowing how they're going to react. So group 1 and group 2 are both incredibly reactive. Group 1 more so, the most reactive on the planet. Next up, group 2s that we're looking at here, also reactive, not quite as much. But the predictability is very key, and that's going to come into play when we come over and we actually see our halogens, or our group 17 nonmetals, and group 18, our noble gases, also nonmetals. So this has been our two metal groups that are our dominant members that we're wanting to kind of get to know. Now, on our way over to our halogens and noble gases, we're going to go through our transition metals. Now, we will use transition metals when we're actually doing problems. But the problem is transition metals, they have this ability to be able to react in different, I'll call it states of energy, or they can form different types of ions, which gives them different charges. Again, we can't get into that yet, so it's hard for me to talk about anions and cations and positive and negative charges, but let's just imagine if you're wanting to give electrons away, you become positively charged. If you want to take electrons, you become negatively charged because electrons are negative particles. Give away a negative, become positive. Give away a positive, gain a negative, you become negative. So when we start talking about how these elements behave when they react, we talk about ion formation. Well, whereas group 1 and group 2 metals were very predictable in terms of how they react, as I mentioned, this is the opposite, which means they can do lots of things. All of these metals in this block, in these transition blocks, and these lanthanides and actinides that are pulled out down here, they can react differently depending on their situation. So it's the opposite. You can't pin down and guarantee how a transition metal is going to react. So if I give you a transition metal, or Ms. Harris gives you a transition metal in a problem, we also have to tell you the exact state of that transition metal in terms of how it wants to react. What kind of charge does it want to form in order to react with something else? That is required. If we want you to write a formula, you've got to know what kind of copper you're dealing with. Okay? It's not enough for us to say, here's some nickel, react it with chlorine. We have to say, here is the specific type of nickel in terms of its charge and how it wants to give or take electrons, and now react it with chlorine. We have to give you the details, okay? So it's not that they're evil. We kind of give them the bad name of being, frustrating, because we like things that we can peg down as predictable. We like that. But it's just the way it is. We will get into a little bit about why that is, but you're going to become very robotic about being able to very easily and effectively solve problems with transition metals because you're given all the information. If we don't give you information, you're totally in the dark and you can't work those problems. So we will use the very, very trickstery transition metals. Trickstery is not a word, but I like it now. But we'll use these, but we have to tell you all about them. Okay, so they're called transition because obviously as we move from our very predictable metals on our journey over to non-metals, we have to go through transition metals. And so you'll start to see trends slowly forming as you move in transition metals. until you are in territory that is not metallic anymore, okay? So this is a very basic pointer. Just know if I were to grab a sample from anywhere in these transition blocks, it's going to be an interesting ride, and you have to know information. That's not a textbook thing. There's a few different ways that we can do that we'll play a game with and be able to figure out, but that's the overall theme of transition metals. Gotta have information, gotta have details, because they can shift and change on you very quickly, which is not a problem as long as you know, okay? Now, halogens are nonmetals, clearly. So I did not, here's our halogens. They are group 17s. So group 17 halogens. Just like I referred to our first two groups as group 1 and group 2, most of the time I'll call group 17 halogens. Go figure. Instead of talking about group 17 nonmetals, I'll just say halogens. That's just habit that I've come to do. But they're important because just like these were predictable, very predictable in their behavior in the metal side, these are most, kind of flip the script and make it the opposite. These are the most reactive nonmetals. So they're kind of like the group 1 of nonmetals, but they're their own group 17, halogens. So if you ever see lots of examples where you have, I'll just use the highlighter, when you have group 1s that are hooking up with group 17s, and you see that a whole lot, there's a reason. Because your most reactive metals are getting together with your most reactive nonmetals, and they both are very enthusiastic about that. And you'll also see a lot of 2s getting together with 17s. All the reactivity, and you'll see group 16s as well being reactive. So you see a lot of interaction there between these metals and nonmetals, specifically in these very reactive groups. But they're the most reactive nonmetals. And they, whoa, that is not a pen. Okay, they're gases, and a lot of them are diatomic. So you have your fluorine, chlorine, bromine, iodine. In England, they'd say, or in the UK, sorry, they'd say iodine. But these are all very, very common, very reactive, very, very important nonmetals that are also diatomic. So that's our halogens. So I'm going to kind of dish over this real quick. 13 to 8, if you Google periodic tables, you'll see family names for these. So you'll see very interesting family names for them, but sometimes they are given some identity, sometimes they aren't. We're kind of glossing over because they are not as predictable and getting off the ground. We don't need that. And also sometimes you'll start with nonmetals at the top of a group, and by the time you get to the bottom, you have metals. And so in this case, metalloids, but again, if you change your state there, that's not very predictable. So these kind of their own thing. So we are clearly focusing on the predictability, halogens. So group 17 is what we want you to know now. So last but not least, group 18. Let's keep our train going. Group 18 are noble gases, LE, sorry. We call them noble gases. They're the snooty, snobby elements because for whatever reason, they're the end of our periodicity before we wrap back around again to the next row. And just a quick 101, because we'll get into this a little deeper. We have been obsessing over families and columns, but our rows are called periods because they're like typewriter characteristics. You'll see trends developing as you move across a row, and then you kind of typewriter back around and start over. And that's how our patterns roll. So we call that periodicity. That gives us periodic table, and therefore we call these periods. They are numbered 1 through 7. So you don't have to spend a lot of time wondering about, hey, what are they called? What are their names? Nope, 1. So period 1 has hydrogen and helium, these two. Period 2, we have these 8 elements. And 3, so you can see how we roll there. So just because there's not anything here, we don't actually fictionalize anything. That's just the way period 3 is. It has these 8 elements. So it becomes a very interesting story with the promise of electrons in the future that are coming. So there's a reason we can force, in really weird conditions, we can make noble gases react with other things. But for the most part, they are completely non-reactive. They do not want to interact with any other atoms at all. They are totally happy. And in our natural state, we find them completely alone. They don't need to be diatomic. They are just loners, total loners. And that is because trying to use great human adjectives. I'm going to say content, happy. It's hard to know. I'll dabble into the electron world and just say that they have the most desired arrangement of electrons in all of their electron shells and levels, however many that may be, from very small with helium to very large. So they have whatever secret we're keeping from you, the way electrons are arranged are optimal and perfect in noble gases for total, when it comes to reactivity, happiness. All these other elements are reacting in order to try to feel like they are optimal and like they are full and they have the most desired arrangement. They don't. Noble gases, krypton, radon, xenon, all those good things. Helium is a noble gas too. They all are just that way, okay? They're just that way, and therefore they don't go looking for any reactions. They don't need them. Everything else is out reacting with all these other things, if they would do, in order to try to get a little bit of that identity. They can't become these, except they can react and interact in a way that makes them, I'm going to use the word feel, because that's just what I do, but it gives them a sense of optimal arrangement, even though it's not true. So if an element can form a bond with another element, and whether they're giving or taking or sharing electrons, those elements interact in order to kind of get a closer feel and arrangement towards noble gases. That's what they're doing. So that's really the motivation for the game that we're playing here in terms of why these things are happening. It's not random. There's a method to all the madness of why the things are bonding. But at the end of the day, these are just sitting watching everything else try to be like them. Hence, noble gases, snooty, snobby things. So there you have it. You have group 18, noble gases, most non-reactive substances, period, but all nonmetals. And then we have all nonmetal halogens, group 17. Those are halogens, so know the name. So this is all vocabulary. That's all major big-time player diatomic gases. Transition metals are just totally unpredictable and all over the map, and so we have to pin those down for you if you're going to work with them, because they can, depending on the moment and the need, alter how they bond and what they want to do. And then we come home sweet home to our very predictable group 2 alkaline earth metals. and that are very active, but not quite as reactive as the group one, the king of, or queen. I should not mix nobility and king queen terminology in this situation. Sorry. The most reactive families. Group 1, alkali metals. Group 2, alkaline earth. So keep all those names in your head. So we might throw out alkaline earth, but we're talking about group 2. Alkali metals, group 1. And what makes them important. Okay? So that is just a quick hit on our major groups we want you to be familiar with. Like I said, periods will come, but we just number them 1 through 7. And that has a very important commonality, but the relationship between our groups is much, much closer and much, much more telling. This is a bigger, broader, still very important, but a bigger, broader relationship if you're in the same row as another element. It means something, except not nearly as much as being able to predict how you'll react if you're in the same group or family. It's a closer relationship. So there you have it. I'm sure you'll now change the world even further, better, and in a more inspired fashion.